this fact that there are different models for the same chemistry. So we just talked about how sometimes somebody would intentionally leave out known chemistry out of a model for various reasons. Maybe to make it easier for the computer to solve, maybe because easier for them to understand it. Maybe it would be because they don't have the parameters for the other species and reactions, and they can't be bothered to try to figure out what they are. So those are different reasons why you might have it. And of course, it could just be ignorance. So you might not be aware of the other reactions and species. So I have a view about this, my own philosophy. Modeling is about philosophy. It's very important. It's like trying to understand what do we know and what are we trying to accomplish. It's very important to think about that when you're doing modeling. So there's this ideal of the perfect fidelity model. So we think that there is a model that exists, I just don't know what it is, that has all of the species, all of the elementary step reactions, all the thermo, all the rate coefficients with the true values for everything. And we think that if we had this perfect fidelity model and we ran that model, it would make predictions that would exactly match what we measure experimentally within all the error bars of the experiment. Right? So this is like the idealization. And for some cases, like for example, hydrogen, oxygen, so far in the history of the world, people have only found 20 reactions that happen in that system. So they only think there's 20 reactions, there's only 12 species, and that's it. And they think if you have a hydrogen oxygen system, that's all there is. And they know a lot of the numbers with a lot of decimal places. And so you think that you might be able to get close to this perfect fidelity model. But in fact, even in that case, they know some experiments that it doesn't predict correctly. And they know a few of the parameters are not known perfectly. So it's not yet perfect fidelity. For most of the other systems we encounter, we're far from it. We're not even close to perfect fidelity. Okay? But you think that there is such a thing exists. So that's my mental picture, is that the reality exists. There really are reactions occurring. There really are all these species. They really have thermochemistry values. They really have rate coefficients. They're all really reacting and doing stuff. And if I was just smarter, and if I had better computers, and I had better experimental ways to probe things, I could see it. And I would actually see what the real model is doing. Okay, yeah, right?
Parameters aren't known, or is that like they don't fit modified or Arrhenius type, or the models that we kind of fit these parameters into?
I think it's a complicated story for the hydrogen oxygen. I think it's that some of the parameter values are only known to one significant figure, and they should be known to 3 to give good enough predictions. Some of them, the K of TP expression is quite peculiar shape, and the way they're fitting it might not be right. So it's something about that, but I think that people don't know exactly, and that's why they have disputes about it. It's also possible that maybe there's just some additional reactions and additional species that they haven't discovered yet, but mostly they know it. Okay, then there's this next level. This is where my group works a lot at. It's called the detailed chemistry level. And this is a human attempt to try to get to this towards this high fidelity model. And we'll have many but not all of the species, many but not all of the reactions, and we'll have all the best known thermo and rate parameters. And the idea here is to try to really represent what we know. So this is representing what do we know about the chemistry. And today's full detailed model is basically saying what humans know about the system right now. All the numbers as best we know them, all the reactions and species and products as best we know them. And we try to write it down. And in some ways, it's an expression of the community's knowledge about some system. And if that model does not match the experiment, it's highlighting the weaknesses of our current human knowledge. And then it suggests you might do some improvements, try to learn more to make a better prediction. But these models can be quite large and complicated. And so if you're using them, for example, in an engine simulation, your computer may not be able to handle it. Also, it can be a major headache for the people making these models. And my graduate students are nodding their heads. And so it's a lot of work to figure out all these numbers and all these reactions. And there can be a lot of different reasons why some of your numbers might be wrong. And then it might take you a long time to figure out why. And so there's a whole project. So in the chemistry world, this is a whole project about trying to make sure we understand the detailed chemistry. There's another level that are the reduced models. And this one could be an approximation to the detailed chemistry. So if somebody wrote down a detailed chemistry model, has 1,000 reactions, and you have a computer program that can only handle 35 reactions. Then you say, well, I got to figure out some 35 reaction model that emulates certain behavior of this 1,000 reaction model good enough for the observables I care about. So maybe I care about in my engine, all I care about is the heat release rate or NOx production or something like that. And therefore, I just make sure my small model, my reduced model, emulates that well enough, and I don't worry about the fact that it mispredicts formaldehyde, because currently I'm not care about formaldehyde. Often when you do this, you end up with rate expressions that are not elementary step. They're not mass action law. That's one way to make your reduced model flexible enough that it can represent a very complicated situation with a small number of equations. And so, for example, if you use quasi-steady state approximation to simplify, which is a common thing to do, you'll end up with expressions which don't fit the elementary step law. And then there's empirical models. These models are designed to be based 100% on experiment. They're based, and usually, often, only on the experiments measured today in my lab by me. So I measured, in my master's thesis, I measured 27 observables. I want a model that contains those 27 things. I don't want to worry about reading all the literature about every other reaction that might be occurring in my system. I'm not really into chemistry that much anyway. All I want is to be able to predict my 27 observables, because that's what I care about. And the chemist can worry about formaldehyde. I don't care about formaldehyde. All I care about is ignition delay or whatever my thing is. And so those models can be completely empirical, and they really have no relation to the true chemistry at all. They're like fitting forms. So we measure things, and often we say, let's make a log-log plot and draw a straight line or something. Okay, it doesn't mean that we really think that these two variables, the log-log plot is perfect, right? But it kind of gives us a good enough prediction. And here, the key issue is trying to keep the number of parameters small enough that you can actually determine them from your limited experimental data. So you only have 27 experiments, then you can't have 57 parameters in your model that you're going to adjust, right? Because you only have enough information at most to determine 27 parameters, and really maybe only 5 if you have 27 data, right? So you're going to try to figure out, okay, I've got to write a model that has 5 parameters or fewer. And that's the main constraint, is to keep the number of parameters small enough that you can determine them. And this requires a lot of cleverness to figure out what kind of functional form that with such a small number of parameters could actually represent my observables. But then trying to connect what this is to that, this could be quite a long reach. These are really different things. On the other hand, if you have a detailed model that really works, you should be able to predict these experiments and make the same kind of plot and see does that empirical form really work or not. Now, the reality is that often multiple models have been created for the same system with different numbers of species, different numbers of reactions, different forms of reactions, different thermo and different rates, everything different. And so for the poor student who first gets into a system, this could be a total headache, because you do a literature search and you see, oh man, there's 17 different reaction models for the same system. And as best I can tell, they should all work. But then when I actually run them all for my experiment, they're all wrong. This is the most common situation, right? So now you have 17 things that the literature tells you should work, but you know that none of them work. And now you have to figure out what to do. Yeah?
Sometimes it is specific to the design, like Werner. I know X is specific to the design of the Werner. You have no ways of determining what are the letters I know X. It's specific to the Werner design.
Yeah. So the experiment, whatever experiment you're doing, it could be a burner, it could be whatever, that the experiment constrains what you can measure, and you have a limited ability to measure things. And also, when you try to solve, if you start with a detailed model, the person who wrote the detailed model had certain reaction conditions in mind. If they don't include the reaction conditions in your experiment, then you might expect that the person left out some reactions or species, or didn't make sure the numbers were good in the region you care about. If the reduced model can be even worse, because the person making the reduced model is making for a very specific application, and if it wasn't your application, then there's no reason why you would expect it would work. And the same with empirical models. If somebody has an empirical model for a shock tube experiment, and then you try to apply it to your burner experiment, you have to be lucky if they match, because it's like, it's just an empirical thing that the NOx produced in the shock tube of these conditions might have really no relation to the NOx you get in your burner, which has recirculation and who knows what else. And so trying to keep this in your mind, Now, it would be good, and you should do, is when you write a model, please write at the top of the model, in the comment line, the name of the model, your restrictions of what you think this model is good for. Because you as the author of the model, you have the best idea of how this model was designed and what it was supposed to be able to predict. And none of the models can predict everything at all conditions, right? So you want to write down, I made this model for high temperature, for pressures less than 1 atmosphere, to try to predict NOx. And therefore, people should believe that if they're running a high temperature experiment less than an atmosphere and trying to measure NOx, they should be able to take your model and trust that it should be pretty good, because you certified that it was good for that. But if they're actually trying to predict low temperature aromatic formation at 20 atmospheres in a homogeneous reactor, then maybe they're out of luck, right? So, and they shouldn't, they're misusing your model to take your model and try to use it for a completely different application. But if you don't specify at the top what it's good for, then the poor student comes along next, has no idea. And so they have these 17 different models, and they don't know that really 14 of them are completely inapplicable to their situation. And then the other 3, they should predict his result, and they don't. And that means that the models they should work, but they're wrong. And that's where we have a chance to learn something. But the 14 that are not supposed to work, of course they're not going to work. And no matter what you do, they're not going to work. So there's no sense spending your time on the 14 that are not supposed to be applicable to your situation. So this is where, if the person doesn't write it in the model description, it's really important to go back and read the original paper, because usually there it'll be quite clear in the paper what the person was targeting at and what ranges they thought this model was good for. And then you can see, is it applied to my situation or not? All right. So now we have another philosophy question. In the models, we always have these species, like we have H atom, or we have benzene, or NOx. There's species that we have in the model. What do we mean? What is it? What is a species? Fundamentally, what is it? Talk to your friends. All right. I can see a lot of you look completely bewildered. Maybe Ryan, do you want to give an answer?
Well, I think it points to the idea is that, like, if we think of a species arrangement of atoms, there'll be wells of potential energy. And this question points at, well, how different do these species have to be different, right? I mean, if we rotate a methyl group, maybe we'll get 3 different wells, of potential energy. But are those really 3 different chemical species? Like, to define chemical species, for them to be distinct, do they need different bonding patterns?
Okay, so Ryan just gave the theorist's view about this, that what a species is like a certain arrangement of the atoms. So we have a species, some chalk. So we can have a species, and we always say for a species typically what the stoichiometry is. How many molecules are there? How many atoms are there? So suppose we have C2H4O. Okay, this would be a species, and if you had a high resolution mass spec, you could measure a species like this by its mass, right? You look up the atomic mass of different isotopes of carbon and hydrogen and oxygen. You get certain masses. If you had a really good resolution mass peak, you'd see that there's some species there. So that's one possibility, but these guys could actually be a lot of different things. So for example, this could be CH3CHO. We call it acetaldehyde. Okay, that's one molecule that has this formula. This thing could be this thing, CH2CHOH. We call that ethenol. That also has the same formula. And there's other things you could write also, different arrangements of the atoms. So, and then this guy has, say, a single bond. And the torsional angle of the H's here with respect to this guy. So let's see if I draw that. So here's my carbon. There's an O and an H. And then behind it are 3 H's on this guy. And these guys could be, like this H could be lined up with one of these H's, or it could be cocked so that none of the H's are on top of this, lined up with this H. And they might be, you might think of them as different species too, right? And so there's many, many different arrangements of the atoms, and we have to figure out which ones we call a species, all right? Now, from the point of view of the theorist, it's all about where the atoms are. How about from the point of view of an experimentalist? How would you, as an experimentalist, think of a species? How do you measure it, right? You guys measure species, right? NOx. Some of you guys, who here has measured NOx? Anybody? Okay. You measured NOx IR. So, okay, so you looked at a certain IR wavelength, and you knew that NOx or something had a absorption there. And so you said, when I see that peak go up and down in my spectrum, then I'm saying my NOx level is going up and down. Okay? So that's a operational definition by a certain absorption feature. And that absorption feature turns out to be quite specific, that it's only certain arrangements of the atoms would have that absorption. And some things that we would call NOx don't have the absorption. So NOx is actually like a mixture of NO and NO2. And you use a thing called a NOx sensor. It tells you the sum of those two. If you do the IR, it's just telling you one of them. So if you're looking at the IR stretch of N double bond O and NO2, you're seeing something that's proportional to a certain NO2 in a certain vibrational state will have an absorption there. And so that's a much more specific definition of the species. Same thing if you did here, if you were looking at the carbon, the CO double bond stretch in IR, that would really tell you about acetaldehyde. It wouldn't tell you anything about this because this guy does not absorb at that wavelength. So then you would count them as two different species from the point of view of an IR experiment. But in the mass spec experiment, they all C2O4HO. They'd have the same mass. So you might call them all the same. Does this make sense? So your definition of a species it has some ambiguity both theoretically and experimentally. So experimentally, you have to define exactly what you're measuring, and you'll get different results, slightly different results, depending on how you measure it. If you're doing it theoretically, you have to define exactly which geometries you mean, and somebody else might choose to make a different choice of geometries to count as a species. And they would get a different result. This is super important for making a model, because a model is all about change of species. You have to have an idea of what the species are. So the experimental view is that my detector response is proportional to the concentration of X. That's the normal assumption, right? And you have whatever detector you got. You have a gas chromatograph, you have a NOx sensor, you have a mass spec, you have an FTIR, you have a laser that absorbs a certain wavelength of UV or fluoresces or something. Whatever detectors you've got, those are the things that you would normally think of as being the response of that detector is proportional to the amount of the species. And so in chromatography, we say whatever elutes at a certain time. I put in a calibration standard that elutes at 22 minutes after I inject. If I run on my sample and I see something coming out 22 minutes after I eject, my first assumption is it's the same species. In mass spec, I look for the mass. Spectroscopy, you see the wavelength. Now, sometimes, as an experimentalist, you're aware of interferences. That means you're aware that two different species give me the same signal. Signal at the same wavelength, signal at the same mass. And then if I'm aware of that, either I report the signal there as the sum of the two species, or I might do another experiment to try to deconvolute them, to do some measurement that separates them. If I'm not aware of it, I might just report it as the species I thought it was and not be aware. So in chromatography, I do chromatography a lot. You have a peak. I think the peak at 22 minutes after injection is hexanol. And I might not be aware that there's also some other molecule that elutes at exactly the same time. And so I wouldn't know that my signal might be spoofed by this other species. Okay? So that's the experimental problem. The theoretician's problem is a little bit different, is that they have to define what geometrical arrangements of the atoms are we going to call the species. So, I might say something is OH if an O atom is next to a H atom with a certain distance, and all the atoms are more than such an amount distance away, then I call it OH. Okay? But there's some ambiguity about which number should I choose here. And another way to do it is I can do a calculation of what's called the potential energy surface and figure out things that are bound together by a certain amount. I'll call them a certain species. I would say that all these definitions are a little bit inconsistent. And the same problem is a much simpler problem. So for example, suppose I want to know how many people live in Princeton. I can compare the number of persons in Princeton today, or I could take the year-round average number of people in Princeton, or I could take the residents of Princeton for tax purposes who pay taxes, or the people in Princeton that were counted by the census the last time the census taker came here, or the residents of Princeton metro area. And all these numbers are different, right? So even a simple thing like how many people are in Princeton is an ambiguous number. The same kind of thing happens with molecules. So, how much hexanol I have in my sample might depend on exactly what I define as hexanol, how I measure the hexanol, and can have some ambiguities in it. All right. This turns out to be super important for kinetics, because if I change the definition of the species, I have to correspondingly change the rate coefficients that connect them. Right? They're sort of one-to-one. Because what I'm doing in species is counting how much I have of something. And when I'm doing rates, it's how much of this stuff is turning into that stuff. It means I implicitly have to know how much of this stuff I had. Right? Otherwise, I won't get a different definition. OK, now the theoreticians, a lot of times, they decide the best way to do this is by considering the potential energy surface. So let's see if I can draw a picture of this. Let's go back to this example here. I'm doing my chalk. So I can plot, say, the OH bond distance and say the CC bond distance. So this is how far apart the two carbons are. This is how far apart my O is from an H. And if I have small OH distance, like here, and also a short CC distance, I'll have a valley over here in the potential surface. So over here is the structure that I would call ethenol. Okay? And anything that's in a certain region here, any structure that I observed that has short CC bonds and short OH bonds and has this formula, C2H4O, I might call it ethenol. And then over here, there's one with a longer CC bond and no short OH bond over here. There's some region, and I'm going to call this acetaldehyde. Okay? And there's a potential energy surface. That means that there's a certain geometry where the acetaldehyde atoms are their preferred arrangement with the lowest possible energy. But the thing vibrates around, so there's actually a region of potential energy around this valley. So here's the spot that I call ethenol's. It's called the equilibrium geometry. And here's the equilibrium geometry of acetaldehyde. But actually, anything in this whole region, I would call it. And then I'd say that these two guys, the two contour plots, come up to a mountain range that sort of divides these two. And things on this side of it, I'm going to call acetaldehyde, and this side of it, I'm going to call ethenol. Is that all right? Now, I only did show two of the dimensions here, but actually there's a lot of bonds. And so really this is like a hyper contour plot, because there's also all the other bond lengths have to be the right ranges too. If any of the bond lengths were too long, then I would say that that atom was broken off, the bond was broken. And so it wouldn't count as acetaldehyde or ethenol. all right? So the idea is that there's a valley in the potential energy surface of interaction between the atoms, and everything in that valley we'll call the molecule. Now, as Ryan pointed out, sometimes the valley has multiple minima. So for example, the acetaldehyde one, you can rotate around this CC bond, these H's, and there's some little configuration here. So there's actually like, this guy might actually look like this. Several different little valleys. They all look about the same, and they're all like inside a bigger valley. So several different minima inside it. And those would be what we call the conformations of acetaldehyde. But we lump them all together and say they're all acetaldehyde from our point of view. And if you measured it by IR, well, IR is really sensitive to like the CO bond distance, because you're measuring a certain wavelength. So it would be a cut of these guys that all have CO bond distances in a certain range. They would give a certain IR absorption. And if the CO bond distance was too far distorted from that, actually its frequency would show up somewhere else. And so we wouldn't count it as outside as measured by IR. All right. Let's see what else we have to say about this. Now, this shape of these energy of interaction, the V of R, we can calculate this from quantum mechanics, and I'm going to tell you more about how we do the calculation later. But the V is insensitive to certain changes in the R's. The R's are the positions of the atoms, and if you, for example, uniformly translate all the atoms in space in the gas phase, it doesn't change the potential energy at all. So certain translations, the translations of all the atoms uniformly doesn't matter. And it turns also that external rotation, if you just tumble the molecule in space, if there's no like electric field in the space, then you won't change the energy either. So it turns out that there's typically 6 degrees of freedom of the set of the R's that you can make motions on that make no effect on V. So V is actually a function only of a subspace of the whole space of R. And we call that interesting subspace the internal coordinates or the normal coordinates. And those are ones that it's a lower dimensional subspace of the full dimensional space of the positions of all the atoms. This R thing is a vector, x, y, z, of the position of every atom in the molecule. Okay? So if I have, in this case, I have 7 atoms, C2H4O. 7 atoms, so there's 21, it's a 21-dimensional vector, R is. And so V is, in principle, in a 21-dimensional space, which is pretty high dimensionality. But 6 of the dimensions are overall external rotations or translations, so it's actually only a function of 15-dimensional space. Still pretty high, but at least a little bit better. Now, in classical mechanics, if you have a thermalized system, the probability of the system being at position R scales as this Boltzmann factor. And so that's why the valleys are very important. The regions with low V of R are much more likely to be observed than the ones with high values of V of R. Okay? And so that's why we define the molecules as basically near the valley bottoms. And if you do an experiment like with spectroscopy, most of the population of that species will have geometries near the valley bottom, and they'll have the spectra that correspond to near the valley bottom. And that's what you typically observe as your main thing. And so most of the time, the system is down in the valleys, where alternatively, you have a big sample that has a lot of molecules of the same molecule. And at any given time, most of the molecules are down near the bottom of the valley, and there might be 1 or 2 of them that are off doing some crazy vibration. If the valleys with low values of V are separated by regions with high V, that means that the ones that are stable are separated by things that are very unstable, then we would say that they're 2 different species, and that that region of the high V is like the natural dividing region. So here we have this over here is ethanol, over there is acetaldehyde. Somewhere in here we have very high values of V, and we could draw dotted lines. We're not sure exactly where. It could be like this. It could be like this. Somewhere over here is the region that's the boundary between geometries that I would call acetaldehyde and the geometries that I would call ethanol. Is it clear? Yeah. And then once we define that boundary, then we could define a reaction, because the reaction is going to be something that changes geometry say from here to here. So the reaction, this reaction is actually a pretty important reaction. And that reaction corresponds to motions of the atoms that move this H over onto this C and change the bond lengths to make it to be like acetaldehyde. And those motions will take you through this region of high potential energy before they end up in the valley of low potential energy of acetaldehyde. All right? Yeah, and you'll see pictures of the structure of a molecule where they give you the bond lengths and the bond angles and all that kind of stuff. Those things are what are called the equilibrium structures. Equilibrium structures. And those are the minima of E of R. But they don't actually represent the true molecule. The true molecule always has the atoms wiggling around. And so if you look at ensemble, you won't find any of the molecules that have exactly the equilibrium structure. You'll find them, they all have different small distortions around the equilibrium structure mostly, and a few of them will have big distortions. All right, once we've figured out how we're going to define the species, then that's going to define the reaction, because it's defining the boundary between two species, and then crossing that boundary is what we mean by a reaction, is when the system converts from one valley to the other valley. And the rate of the reaction is the number of trajectories that move the atoms from geometries that we would call A to geometries we would call B, minus the reverse rate from B to A. And all these trajectories cross the dividing surface between B and A. So we can count them there. And we don't have to look down at what's happening inside the valley. So the molecules are wiggling around inside the valleys. We don't care. We only care about the ones that cross. So if I look at an ensemble of ethanol systems, and I just take a snapshot, I'll see some of them have geometries here, some here, some here, some here, some here. And maybe I see one that's crossing the boundary. And that's what I care about, is how many of them are crossing the boundary at the moment I take my snapshot. And if I do this over and over again, and I count how many are crossing compared to how many are down here, then I can infer what the rate coefficient is. That's the idea. So the analogy is, if you want to figure out what's happening, say we're, instead of counting how many of the molecules are in geometries we call ethanol, instead we say, let's count how many cars are in Manhattan. Okay? So I mean, a more concrete thing. So we look at Manhattan, and we could count all the cars. Well, one way to do it is to go and try to look in every parking garage in Manhattan and try to count up how many cars there are. But if you all care about is the rate of change, we can just count how many cars are crossing the bridges and tunnel. And so I have a nice picture. Here we go. So here's the rate coefficient. There's the map of here's New Jersey. Sorry. Uh-oh. Here we go. This is New Jersey. Here's Manhattan. There's some bridges. You see a bridge there, and there's a couple tunnels here and here. Here and here, sorry. There's a bridge. Okay, so that's if you want to have a rate for going from New Jersey to Manhattan. A simple way to estimate it would be go to the toll takers at the bridges and the tunnels and count how many tolls did you get. How many tolls today? And that's how many cars went from New Jersey into Manhattan. And then you say, look up the registration, how many cars are registered in New Jersey. And you can take the ratio of number of cars that cross from New Jersey to Manhattan today, divided by number of cars in New Jersey. The units of that is per second, and that would be the rate coefficient per second of how many, or per day, how many per day go from New Jersey to Manhattan. And you can do the reverse. Currently, they only collect tolls when you go into Manhattan, so that's all I can get from the toll information. But you can stand on the other side of the river and look at how many cars are leaving across the bridges and across the tunnels, and you can get the rate for the reverse reaction from Manhattan to New Jersey. All right? Let's see. All right, so that's species. All right, so now let's generalize that. Suppose we have a large ensemble systems. They each have atom arrangements we calculate as characterized as species A. So for example, ethanol. And then we select the positions of the atoms to be inside that well, in that valley. So we call them species A. And we select them with momenta P. And we draw this from a Boltzmann population of the momenta, of the positions and the momenta. So it's Boltzmann weighted. So the ones that are down in the bottom of the valley with small momenta are more likely, and the ones that are up on the walls of the valley with high momenta are very unlikely by the Boltzmann factor. And we want to calculate what fraction of all these systems are going to convert into species B in the next time period, delta t. And that's sort of how many of the atoms are going to move across the dividing surface to reach the geometry we call species B. And we take the ratio of this fraction divided by the delta t, that turns out to be the expectation value of the rate coefficient. Okay? So that's the theoretical conception of what a reaction is. Right? Experimentally, what you do is you turn your spectrometer on, you turn it on the C double bond O absorption line, you start out with the phenol, and you see the rate at which that line grows for acetaldehyde appearing, and you divide it by how much ethanol you had to start with, and that rate, number of acetaldehydes appearing per second, divided by how many ethanols I had to begin with, that would be your expectation value of the rate coefficient for the reaction. All right, so there's our picture. So here we have our thing. It's the average number of cars entering the Hudson River tunnels and bridges per day, divided by the numbers of cars in New Jersey. That would be a way to estimate the rate coefficient. Here's the classical mechanics formula written out longhand. And let's see if I can explain this, what this is. So you need to define a boundary, a bounding surface. That's the boundary between the two species A and B. So that's like this dashed lines I've drawn here. You have to decide which one you want to use. And you define a function S of R so that S of R is equal to 0. The 0 contour is the one that's the boundary. And things with S less than 0, negative values of S will be ethanol, and positive values of S would be acetaldehyde. Okay, so you define your boundary surface, and you say if the Heaviside function of S of R is equal to 1, then I'm in region B. If it's otherwise, it will be in the region A. And I assume that Boltzmann population of the initial positions and the momenta, and this is the formula for Boltzmann weighting, the Boltzmann factor, whereas the energy is a function of the position and momenta, divided by the integral over all the possible positions and momenta you could have. And this is the energy expression. It's the potential energy plus the kinetic energy summed over all the atoms. And beta is 1 over kT. And this integral is related to a quantity that has a famous name called the partition function. And it's this integral divided by Planck's constant to 3n just by convention. This is a way to make it dimensionless. A Q is a dimensionless number. And so there's the rate expression. And you basically have an operator, F, that's the flux operator. That's the flux of how much stuff is crossing from A to B. And the rest of this is just Boltzmann weighting to get the average. F, if you work it out, comes out to be a delta function of S, which means that I only count things at the boundary. So I'm only counting the cars as they go through the toll plaza, past the toll gate from New Jersey to go to Manhattan. And I count them by how much their direction as they cross it lines up with the normal to the boundary. So if they're really crossing the boundary, they count a lot. If they're just going at a glancing angle, then their velocity doesn't count very much towards making products. And so this is the overall expression. So this is the true expression, classical mechanics, for what a rate is. Okay? And the key thing is to define the bounding surface, and then you can count how many things are crossing the boundary surface. Now, in a very special case where you cleverly choose the bounding surface, this is the special way, which I wrote down here. If you cleverly choose it just exactly a certain way so that you have one of your coordinates is the normal to the bounding surface. So it's the direction that crosses it, and all the other ones do not cross it. Then you can reduce that summation to just one term, because there's only one term that has motion, and that one coordinate changes the value of S, which means you cross the boundary, and all the other motions don't do anything. Then that really simplifies the formula. And in that case, you can analytically integrate over the one special coordinate, and you end up with this expression, very simple way to write it down, where this thing is defined to be, it looks like a partition function like before, except it's special that we've left out the special coordinate. So there's the one coordinate that crosses the boundary, Q star and P star. We did those integrals analytically already, and the rest of them are here. Okay. And we moved one of the factors of h. We left this one in to leave this dimensionless, and we pulled out one value of h here, and that's why it's here. And so this is kind of a cool expression, actually. So this thing is saying there's like a prefactor, a natural prefactor that's kt over h. All fundamental things, just depends on the temperature. And then there's this other factor that's special about the actual reaction, and that one includes the barrier height, actually, implicitly, because it depends on the potential energy at q star equals 0, which is at s equals 0, on the boundary. And so you're at your boundary, you're up in the mountains. Here's these two valleys. There's mountains in between. The boundary is somewhere in the mountains. And there'll be a minimum energy in this mountain region, and that will be what we call EA, the effective barrier height. All right, and that's going to show up here as the minimum. The minimum over all the Q's of V will turn out to be that minimum energy. That'll be the minimum energy it takes to do the reaction, classically. All right, now that simple formula is too simple because it turns out you can't actually do that separation of variables the way I said so perfectly. So the real dividing surface turns out to be it's a curved hypersurface, very complicated. But often, most of the flux comes through a few special areas. So for example, in the Manhattan example, if I only look at the George Washington Bridge, the Holland Tunnel, and what's the other tunnel? Lincoln Tunnel. If I only look at those three, I'm getting like 99% of all the flux of cars. Some cars might go there on a ferry. Right? Cars could be dropped in by helicopter. There's other ways cars could get to Manhattan from New Jersey. But 99.9% of the cars are going to take one of those three routes. So if I want to get a rate from New Jersey, if cars moving from New Jersey to Manhattan, that's a really accurate way. It's just to look at those three toll plazas. I don't need to consider the entire dividing surface. So I don't have to look everywhere in the Hudson River because not that many people are going to drive a car on a boat across the river. Okay. And this happens the same with molecules, that there's certain regions in the path connecting between the two molecules. There'll be like a low energy path. And almost all of the flux will go through the low energy path because the Boltzmann factors are so much more favorable. And the high energy ones, there are some, it's possible to react over crazy trajectories, but it's very rare. So if you leave them out, you won't be that wrong. So if you just sum over the low energy path ones using this formula of the n low energy paths, you actually get a pretty good expression for the rate. And that's actually what's done in practice to calculate rates. Now, I'm going to tell you a little bit of how to do this, but you really, if you want to learn about it, you should take Dr. Klippenstein's class in the afternoon, because he's like the world's expert on how to calculate these Q's as best you can, and for every possible case. So I'll kind of sketch it out. But if you want to really do it, take the other class. All right. Crucially, if you just change the definition of species or change the definition of dividing surface, you're going to get a different number. Okay? So, if I counted number of cars going from New Jersey to New York State, that's a different number than number of cars from New Jersey to Manhattan. Okay, a lot of cars go from New Jersey to Manhattan, but there's some other ones who go up the Garden State Parkway and go to New York State, or go up the Palisades Parkway and go to New York State. And so I would have left them all out. Some of them go through Staten Island, right? There's a lot of ways you can get to New York State besides going through Manhattan. And so if you do change your definition of your molecule, so for example, if I change from my molecule that I care about being acetaldehyde to being C2H4O, that's a different thing. And I should expect a different rate coefficient. I'm harping on this because this is a common error in kinetics, in comparing kinetics with experiments, is like comparing two different things. If somebody has one definition of species and somebody has a different definition, you're going to get a different result. And you got to expect it. And so you have to really pay attention to this. Also, if you're only going to count the cars that parked overnight in Manhattan, you're going to miss all the commuters, right? The commuters come in, they drive in from New Jersey in the morning, they drive out in the evening. If you only count the cars at nighttime, then all that flux should not count, because they all came and went. And all you care about is the ones who stayed overnight. That's a different thing. So that's like in in experimental kinetics, you can have things transiently form something, but if you only care about the ones that live long enough to make it through your GC, that's a different thing than seeing the transient guys that are formed, because they might form and then go away, where other guys are formed and stay. They both went through the dividing surface, so if you're doing it from the theoretical way of calculating the dividing surface, you'll get the higher number. It's the sum of all those guys. But if all you care about is really the ones that stay, then you have to figure out a better way to measure it or a better way to calculate it. Another issue is this thing about the measurement method. So, spectroscopy measures typically one exact arrangement of the atoms, which has a very characteristic signature in the spectroscopy. Mass spec and chromatography are much looser. They lump all kinds of things together, and you measure things together. And also, typically, they work at different time scales. Chromatography, it takes many minutes for a sample to get through a chromatogram. So any molecule that's not stable over those many minutes will not be detected in the chromatography experiment. The mass spec, you have to sample, so it takes longer than typically spectroscopy can be done very fast. So, but then spectroscopy also can have variables. So if you do FTIR, it might take minutes to do a scan, or maybe seconds. But if you do laser absorption, like with a diode laser, then you might be able to have resolution of microseconds. And so you'll see different things. And this is very analogous to the same problem here. And then a lot of times what the theoreticians try to do is try to choose a dividing surface that gives the smallest possible value of the flux, because they say that that might be closest to what the experimentalists care about. So the experimentalists don't care about people who come and immediately leave. They care about the molecules that actually stay, that you'll be able to measure, say, by chromatography. So here's an example. So this is the approach to George Washington Bridge. Okay, so over on the right-hand side, here's the Hudson River. Over here is Manhattan. This is where the toll plaza is. If you go to cross and pay the toll to go to Manhattan and George Washington Bridge. How many of you guys drove through George Washington Bridge on the way here? Okay, so at least some of you guys know about this. There's a horrible spaghetti over here, a lot of roads. It's super easy to get confused. I hope not too many of you took the wrong turn. I've come off here and I lost my battery here. This is Palisades Parkway. If you're in the right lane, you get forced to go to the Palisades and you can't get off for about 5 miles. I've done that and then I have to turn around and get back. Okay, so make sure you're in the center lane or left lane when you come through. Anyway, so this is where the dividing surface is, and I can count the cars here. But I could also define it other ways, and each of these will give you a different number of cars that are crossing. So this dividing surface here is counting the ones that are actually going to cross the bridge, probably, because not too many people are going to go out across the bridge and then do a U-turn before they make it to Manhattan. So that's a pretty good number for calculating how many are going to cross the bridge. This one at the toll plaza, you'd think it'd be the same. It should be pretty close, but they could actually do a U-turn at the toll plaza and turn around. So it's possible, like if people like me, if you went the wrong way, you say, oh my God, I don't want to go to New York. Then you plead with the toll person to let me go back to New Jersey. If you draw the boundary this way, that looks like pretty much the same, right? It's crossing the bridge. But you're also crossing this other road here, the Henry Hudson Drive. And so people that are coming this way on this road, you'll count them for crossing the boundary too. But these guys actually never go to Manhattan because they stay on this side of the river. So you'll overcount how many people cross. If you draw it this way, all the people coming down the Palisades here to the ramp, you'll count them twice. You count them when they cross here, and then they cross again here. Okay? So all the stuff that you see in 2 dimensions on the road network, there's a lot of ways this can happen in a hypersurface. It's a high-dimensional space, and there's a lot of goofball trajectories you can have, and they can go every which way. And if you change the boundary position a little bit, you'll definitely get a different number, depending how you change the boundary. So this is something to just watch out for. Now, a lot of times, a lot of people would choose boundaries that are kind of similar, and they get kind of similar numbers. But you won't get exactly the same number unless you chose exactly the same boundary and computed exactly the same way. And so you see a lot of discrepancies between people's calculations. And I would say that if its discrepancy is bigger than a factor of 2, you should worry about it. If it's less than a factor of 2, it could be for a lot of stupid reasons like this. So also that sort of implies that I sort of have an uncertainty of a factor of 2 right off the bat in trying to compute rate coefficients, because I don't really know exactly how to draw the boundary that well. All right, so this is the end of lesson 1. So most of the elements make solid oxides, which are inconvenient to handle, though, as some people argue in this class, we should maybe broaden our view and think about handling solids. Most of the others, except for carbon and hydrogen, have too low a heat of combustion to be interesting, or else they make toxic products like sulfur. So the problem is that carbon-based fuels make greenhouse gases, and we can't achieve every goal we would like for a transition fuel at once. It's just not possible. There's no elements that would make it possible. So that's a problem right from the beginning. To model the kinetics of the system, we have to know the species that are present, what reactions occur, all the thermo and all the rate parameters. We never know all of that information perfectly. And so the kinetic models are almost always incomplete and always approximate. And because of this, you often get multiple models for the same physical situation. And then you have to decide which models you're going to use. And it's best if you know best about what somebody was trying to do when you started. You need to think carefully about how the species in the model are defined, and also in an experiment how they're defined. And if they're not consistent, then you shouldn't expect them to agree. And then once you have a clearly defined dividing surface and phase space, you can write down the classical mechanics formula for the rate coefficient. And so then the challenge will just be to compute these partition functions. We'll talk about that a little bit later. And if you take Dr. Klippenstein's course this afternoon, that's the main topic. All right, so that's the end of lesson 1. And so let's take another break. And let's meet back here at 11:25.